Good morning everyone, and we're now on the second to the last lesson of the Physics 3, the electricity and magnetism. Today we're going to dive into the fascinating world of alternating currents, or AC for short. We have three exciting topics to explore together. The first one is the phasors and the alternating currents. In this, we're going to learn about the phasors, which are the special tools that help us understand the waves of AC electricity, and think of the phasors as a magical arrows that shows us the strength and direction of these electrical waves. The second one is the resistance and reactance in AC circuits. In this, we're going to discover how electricity faces obstacles called resistance and reactance as it travels through the circuits. And we'll see how resistors, inductors, and capacitors each play a unique role in shaping the flow of electricity. And for the third one, the RLC series circuit, we're going to put it all together and look for the RLC series circuits actually. So these circuits combine resistors, inductors, and capacitance in a special way, creating something interesting behaviors like resonance. So in this, we're going to start by understanding the basics of the alternating currents and how it differs from the electricity we get from the batteries. Then we'll dive into the phasors and see how they help us visualize and analyze AC circuits. And after that, we're going to explore the concept of resistance and reactance and learn how they impact the flow of electricity. And lastly, we're going to study the RLC series circuit, seeing how these components work together to create a fascinating effects in the circuit. Okay, so let's start with the lesson number 1, or the topic number 1 actually. The phasors and alternating currents. So phasors are special tools that help us understand a special kind of electricity called alternating current, or for short, what we call the AC. Alright, let's start with the alternating current, or AC for short. Imagine electricity flowing like a water in a river. In AC, the electricity flows one way, then switches and flows the other way. This happens over and over again. It's different from direct current, or DC, which flows in just one direction, like water flowing straight down a slide. We use AC in our homes for things like the lights, the televisions, refrigerators, air conditioners, and because it can travel long distances easily. So yes, for applications commonly used in households, industries, and the power grids. Next, let's talk about the characteristics of alternating currents. So its waveform is typically represented by a sine wave. As you can see in the diagram, it looks like a wave or an ocean wave in a graph. So that is the alternating current. So yes, AC electricity looks like a wave, and there are some important parts of the wave. So we have the important parameters to think of and to remember also. So the first one is the amplitude. So this is how tall the wave is, showing the maximum strength of the electricity. The next one, we have the frequency. So from the word frequency, this is how many waves pass by in 1 second. So we measure this in hertz, or Hertz, hertz, or Hz for short. The next one, we have the period. This is the time it takes for one complete wave to pass. It's like the length of one wave cycle. And for the last one, we have the RMS value. So this stands for root mean square. So it is a special way to measure the effective strength of AC electricity, making it easier to compare with the direct current. Now let's proceed to the introduction to phasors. So again, phasor is a complex number representing the magnitude and phase of a sinusoidal function. So its representation, phasors are used to simplify the analysis of the AC circuits, graphical representation of the magnitude and phase relationships. As you can see in the diagram, we have the rotating phasor, and also we have the sinusoidal waveform in the time domain. So that is an example of the phasors. Like, again, phasors are like magic arrows that help us understand the AC waves. Now imagine you have a spinning arrow. Okay, spinning arrow. That the length of the arrow shows how strong the wave is, and the direction it's pointing shows which way the wave is going. So phasors, in short, it makes it easier to see and understand what's happening in an AC circuit, especially when things get complicated. So that is the main function and the main definition of the phasors. So do we understand? So let's proceed to the relationship, the phasors relationship to the AC circuit. So what is its goal to the AC circuits? So in AC circuits, we often use the phasors to show how electricity moves through different parts of the circuit. For example, voltage and current phasors. So this phasor shows the relationship between the voltage or the push and the current, the flow in the circuit. So the second example is the phase difference. So sometimes the voltage and current waves don't peak at the same time. The voltage might lead a lag behind the current. So phasors help us see this phase difference, showing us which wave is ahead or behind. So this is the most important understanding how circuits with resistors, inductors, and capacitors work. So in conclusion, so let's have a conclusion first to our first topic before we move on to our second topic. So conclusion and summary, we discussed the key points, the AC and DC, AC versus DC, characteristics of AC, definitions and use of phasors, and the phasors diagrams and importance. So yes, we talk about how AC electricity flows back and forth like a river, creating waves. We also learned that the phasors are like magic arrows that help us understand these waves and showing us the strength and direction to the electricity. The phasors are very super helpful for engineers and scientists how design and work with AC circuits. So does anyone have any questions about the phasors or AC currents? Of course you don't, because you already understand about the phasors and AC circuits because you're very clever, because you're very science students. Okay, so let's proceed to the topic number 2 about the resistance and the reactance. So for our third topic, we're going to learn again the resistance and reactance in AC circuits. So these are important ideas that help us understand how electricity behaves in different situations. Yes. So let's get started and explore these cool concepts together. Now let's have the introduction first to the impedance. So impedance, by definition, in AC circuits is the combination of the resistance, or represented as X, and reactance, represented as X. So first, let's talk about something called the impedance. So impedance is a big word that tells us how much a circuit resists the flow of electricity. So it makes up of two major parts. Again, it is the reactance, and the second one is the resistance. So resistance, this is like the roadblock that slows down the electricity no matter how fast it's going. So imagine you are driving a car in a very empty road, and there are many roadblocks or bumps on the road, and that makes your car moves slowly. So in contrast, the reactance, or represented as X, this is a special type of resistance that changes with the speed of electricity. So there are two kinds of reactance actually. So the first one is the inductive reactance, or comes from coils or coils of wire called inductors. And the second one is the capacitance reactance, or comes from things called the capacitors. So the total impedance, or denoted as Z, is found using the formula Z is equals to the square root of the summation of the R squared and the X squared, or the resistance squared plus the reactance squared. So that is the introduction to the impedance. Now let's proceed to the resistive AC circuit. So now let's look about the circuits with just resistance. So in these circuits, first we have the characteristics that the electricity flows through the resistor, which slows it down, but it doesn't changes the wave shapes, as you can see in the diagram. Now, for the voltage and current, they move together. like best friends holding hands. So this means they are in phase, or they are they're singing the same song actually. So we have there in the diagram, no? And lastly, we have the impedance calculation. So here, impedance is simple because it's just the resistance. So we denote it as Z. Z is equal to R. So the impedance is equal to, okay, correct, to R. Very good. Now, let's talk about the inductive resonance, or denoted as the XL, not extra large, ha? Inductive resonance. So, it is the reactance due to inductors. So, we have the formula XL is equals to 2 pi and multiplied to the FL. F is denoted as a frequency and L is the inductance. So, yeah, this comes with something called the inductor, which is usually a coil of wire. So inductive reactance tells us how much the inductor resists the flow of electricity. So we have the formula. Again, we have used the formula to find the XL, which is the 2 pi FL, where F is the frequency, or how fast the wave is, and L is the inductance, how much coil we have. Now, for the phase relationship, in an inductor, the electricity wave or the current is a bit slow and lags behind the voltage wave by 90 degrees, like it's playing catch up. Okay, so as we can see in the diagram. Now, so since we have a inductive reactance, we have also what we call the capacitive reactance, or the XC. Now, this comes for something called a capacitor. Because it is a capacitor, so it is related to the capacitor, which stores electricity like a tiny battery. Now, capacitive reactance tells us how much the capacitor resists the flow of electricity. Now, we have the formula. We use the formula to find it, or to find the capacitive reactance. So we have the XC is equals to 1 over the 2 pi FC, where F is the frequency and C is the capacitance, or how much the capacitor can store. So the phase relationship in capacitor, the electricity wave or current is quick and gets ahead of the voltage wave by 90 degrees, like it's leading the way. So as you can see in the diagram. So as you can see okay, very good. Nice yan, diba? Quick, and again, makita na to na nag-una ang blue na strip kasi sa voltage wave na to. Now let's proceed to the impedance in RL and RC circuits. So finally, let's see what happens when we mix resistance and reactance in circuits. So the first one, we have the RL circuit. So this has both a resistor and an inductor. So the total impedance is Z is equals to square root of the summation of the R squared and the XL squared. So the current lags behind the voltage. So for the RC circuit, this has both a resistor and a capacitor. The total impedance is Z is equals to square root of the R squared plus the XC squared. So this current leads the voltage. Now for the phasor diagrams, these are the pictures that shows how the waves of voltage and current look in these circuits. So in summary, in the lesson number 2, we have understand the impedance components that help us design and fix electrical circuits better and much safer, especially when you're going to create an electrical circuits here in our house. So okay, let's proceed. Lastly, we're going to learn about the RLC circuits, but sometimes it was denoted as the LRC, but some says it's RLC. So let's use RLC in this case na lang. So yes, RLC circuits series circuits in the alternating current. So this is a special type of circuit actually that has three important parts: the resistor, the inductor, and the capacitor, or the RLC. So that makes sense. So let's find out how they work together. Okay, so let's have an introduction first to the RLC series circuit. So imagine a simple line with three things in it. So we have a simple circuit with three main components. We have the resistor, inductor, and capacitor. So the resistor, its main function is to slow down the electricity, while the inductor, it's like a coil that also resists changes in electricity. Now for the third one, we have the capacitor, or the C, which stores and releases electricity, and when we put them together in a line, we call it a series circuit. So the total resistance to electricity in this circuit is what we call the impedance, or the Z, or denoted as Z. So we find it using the formula Z is equals to square root of R squared plus the square difference of the XL and the XC, where XL is inductor's resistance and the XC is the capacitor's resistance. Now let's proceed to the impedance and phase relationship. So impedance is like the total roadblock that electricity faces. It changes the frequency of the AC. So first we have the inductive reactance, or XL. So this increases with frequency, like the inductor is getting stronger. The second one, we have the capacitive reactance, or XC. This decreases with frequency, like the capacitor is getting weaker. So what is the phase relationship? So in a circuit, the voltage and current waves might not match up perfectly. So the current can either leading or lagging behind the voltage. So depending on whether the inductor or the capacitor has more reactance. Okay, do you get it? Okay, very good. Now let's proceed to resonance in the RLC series circuit. So we have this. Resonance happens when the inductive reactance, or the XL, and the capacitive reactance, or XC, are equal. Makes sense, or they are equal. So it's like a perfect balance between the XL and the XC. So the resonant frequency, or the FR, this is the frequency where the resonance happens. So we can find it using the formula. The FR, or the resonant frequency, is equals to 1 over the 2 pi square root of the LC. Now for the behavior at the resonance, so at this point the impedance is at its minimum, and the current in the circuit is at its maximum. So it's like finding the perfect speed where everything flows smoothly. So that is the resonance under the RLC series circuit in an alternating current. So let's proceed next to the frequency response and bandwidth. So frequency response, this shows us the impedance changes as the frequency changes. So at the resonant frequency, the impedance is the lowest. Okay, so in the bandwidth, this is the range of frequency around the resonant frequency where the circuit works well. So it likes a sweet spot where everything works best. And lastly, we have the quality factor, or denoted as Q. This tells us how sharp or narrow the bandwidth is. We find using the formula Q is equals to FR over the change of frequency, where the change in frequency is the bandwidth. Okay. And now we're on the last slide of our lesson. So the application and the practical consideration, we're going to use the alternating currents. So RLC series circuits in real life, we need use it frequently to to create circuits to power those appliances we need. And actually, we need to think about before we using them, or what we need to use, or we're going to use these components if we're going to use the specific appliances or to light things up in our house. So for the application first, so these circuits are used in things like the radio tuning circuits. So where we need to pick up specific frequencies, like for example, you're going to pick one of your favorite FM radios or AM radios. So it filters the block of unwanted signals using this kind of RLC circuit. Now, for the practical consideration, when designing these circuits, we need to choose the right values for resistors, inductors, and capacitors to make sure they work correctly at desired frequency. Because if your resistor is very low, then your the inductors is not coincident with the resistors weight or the amount of its resistance, and the capacitor is not relative to the inductors and resistors, then your RLC circuits might not work perfectly and might be explode when you're not perfectly choosing the right amount of what we need to use in the specific appliances or the product. So that's it. That is my lesson about the first 3 lessons about the electricity and magnetism's alternating currents, and I hope you learned more about this lesson. And now let's proceed to my co-reporter, Mr. Miss Jamel Jimeno, to continue the lesson about the alternating currents.